All right, so thanks, Niladri. So I'll just start from where we left off last time. So remember, we were talking about the fractional posterior, and so a lot of the things got simplified if you are assuming the fractional posterior. So we'll simply start from there. So just to kind of remind ourselves the basic setup. So we have x1 through xn given theta follows some probability distribution p of x given theta, and theta is in the parameter space script theta. Theta star denotes the true parameter. And we are looking at the posterior distribution of some neighborhood given the data that we observe. So again, we are using the notation x superscript n for the samples that we observe. And we are studying the behavior of this guy as we get more and more samples. So we can do it for fixed epsilon, in which case we are looking at the posterior contraction, posterior consistency. But we also talked about posterior contraction rate, where we look at a sequence of real numbers, positive real numbers converging to 0. Right? So, and we talked about many notions of convergence with respect to which this statement can be true. We'll primarily look at the L1 convergence. Okay. All right. So we are looking at several sufficient conditions that would guarantee this this contraction rate. So for that, the first thing that we started with is the fractional posterior. So we didn't look at the original likelihood, but we raised the likelihood to the power alpha posterior distribution given the sample is really e to the alpha times ln theta theta naught by theta normalized to make it a density. And just to kind of remind ourselves what ln is, it's simply the log likelihood ratio, right? So ln theta theta naught is simply the log of the joint density. So that would be essentially the sum of the logarithm of individual likelihood ratio, p of xi given theta, p of x given theta naught. Okay. And this alpha has to be strictly between 0 and 1. So if alpha is exactly equal to 1, we get back the original posterior distribution. Okay, so what we are able to prove in this context? So this is the result we proved last time. In order to state the result, we also need the definition of the KLV neighborhood. So if you recall what that is, it's simply a neighborhood of the parameter space for which the KL divergence between p theta naught and p is smaller than epsilon n square. And we also define what is called the V divergence. And that has to be smaller than epsilon n square as well, right? And we use the notation B sub n for this guy. Okay, so what we are able to prove is the following. So if the prior probability of Bn is not too small, that means the prior assigns sufficient mass around the true parameter, So this Bn neighborhood is essentially a certain type of neighborhood around the true parameter, right? And the geometry is kind of complex. It depends on the KL divergence, and the KL divergence essentially is dependent on the model that you choose. So this neighborhood is essentially model dependent, but then we also intersect with slightly stronger notion of divergence, which is the V divergence. Again, just to kind of remind ourselves what that is, it's simply what we have for the KL divergence, we simply raise it to the power 2. Okay, so this is essentially the V divergence, and the reason we need it is simply for technical simplicity, because we have been using Chebyshev's inequality, so we need some control on the second moment of the log likelihood ratio. Okay. All right, so just to kind of state the result that we proved last time. So if the prior probability of Bn is greater than e to the negative n epsilon n square, you can even have a constant in here, but the constant has to be global constant. It can depend on p, but it cannot depend on n. So the constant is can be dependent on the model that you choose, but it has to be like fixed. Okay. All right, so if you have this condition, then what we are able to prove is so let's call the numerator of the posterior to be so we can define the posterior probability itself b theta star epsilon n complement given the samples is essentially the integral of the numerator over b theta star epsilon n complement. And let's use the notation n for the numerator and d for the denominator just to kind of simplify ourselves. What we have proven is the following. So if we just simply take the expectation of the numerator under the true data generating mechanism, and we are using the subscript theta naught to indicate that, that's going to be smaller than e power minus some constant times n epsilon n square. That's what we have proven last time. And we also showed that the denominator, without the expectation, so denominator we have a slightly stronger statement. So the denominator is, say, less greater than e power minus some other constant d n epsilon n square with high probability. That basically means this is greater than 1 minus 1 over n epsilon n square. Okay, so this is exactly what we have proven last time. So now let's clarify a little bit about the neighborhood under consideration, because the neighborhood really played a crucial role in order to guarantee that the expectation is small. So the neighborhood that we considered is not just any neighborhood. It's essentially given by a divergence, which is the alpha divergence. So theta such that d alpha theta naught. So again, I'm probably switching between theta star and theta naught here. So we have used theta naught last time. So let's stick to that. So this is the neighborhood that we started out with, right? And again, I'll not define what any divergence here is. So you all know it's essentially 1 over alpha minus 1. Let's just quickly do that. 1 over alpha minus 1 log of the affinity between theta naught and theta. And and this affinity is guaranteed to be less than 1, which makes it a valid divergence, right? So this is what we have proven last time. So now what we are going to do, we're essentially into this situation that the expected value of the numerator is small with respect to some constant, right? And the denominator is not too small with high probability. So you can expect when you take the ratio would be expected to be small. But then you are in this situation that you need to be able to control C and D. Otherwise, you can't really say that the ratio is small. So to do that, what typically is done is that we inflate the neighborhood a little bit, right? So we multiply the neighborhood by a constant. So we inflate the radius by a constant m, okay? And what we are going to argue is that if m is sufficiently large, then we can make the ratio to be small with high probability. And now we can see why making m large will help us, because if we make the radius larger, then the constant will percolate here, essentially, right? It should be m times n. Yeah, go ahead. So this one is the denominator, yeah. N over d. So there is no neighborhood in the denominator, right? So it's an integral over the entire parameter space. So it's free of any divergence that we are looking at. Okay. All right. So this is a very critical point, that if we inflate the radius by a factor of m, the numerator, the expected value of the numerator is small, and the m kind of enters in the exponent, and which helps the analysis a little more. Okay. All right. So what exactly we are going to do? So the numerator has an expectation which is small. The denominator is not too small with high probability. So how to kind of like combine these two? Yeah, go ahead. It depends on alpha, but it's essentially in D. Okay, it depends on. It doesn't really matter. So the denominator analysis is even true for alpha equals 1. So that's again a very important point. So so this is true for any alpha between not 0, obviously, because if you raise the likelihood to the 0, then you'll end up getting nothing, uniform distribution. So the denominator is true for alpha equals 1 as well, but the numerator is true only for alpha strictly less than 1, because we need to be able to define this divergence, which is only good if alpha is less than 1. Okay. All right. So how to combine these two statements? So one is in expectation, the other one is in probability. So how to combine that? Go ahead. Yeah.
My question is that from the last week, I understand that to control the numerator or the expectation, we needed to introduce those alpha things. Okay.
Yeah.
And then now we are saying that I want to increase the radius of that set we define.
I mean, we are not really increasing that now, but I mean,
I want to define it like that.
Yeah, I want to define.
Start like that.
Right.
What happens to the like the proof? Like, do we change anything in that proof statement? Exactly.
No. So this is independent of the neighborhood, right? It's the denominator. So the neighborhood gets entered only in the numerator, right? So there are two neighborhoods: the KLV neighborhood, which is used to treat the denominator, and that's fixed all through your analysis, right? And once we assume that the prior probability is not too small, the denominator is also not too small, that's fixed. So there is no dependence on the neighborhood here. But depending on what neighborhood that you pick here, this statement is going to change. Okay? All right, so we have, let's say, 1 and 2. So how to combine? So we want to make a statement like the probability n over d, let's say, greater than e power minus some other constant, let's say e n epsilon n square, is So numerator over denominator should be is greater than a constant with. So if you're looking at the complement, it should be small than something, right? So how to make a statement like this? Anyone? So it's in expectation, it's in probability. So how to combine that? Yeah, essentially that. So this is true in expectation, right? So the probability that n is large should be small, right? So then we already know that probability that d is large. So we can combine that. And then what will happen is essentially we'll get the intersection of two high probability events, which will be of high probability, right? So so let me kind of like so let me be a little more formal here. So one implies that probability n is, let's say, larger than e power minus. So I'm going to again divide it by a small factor in order to apply the Markov inequality, right? So n is greater than e power minus c over 2 times n epsilon n square. So then by Markov, this would be expectation of n divided by the c over 2. Then c over 2 will go up, but then we already have a c here. So we still have a negative contribution. And this is going to be less than e power minus c over 2 m n epsilon n square, right? Okay. So then these two will force essentially the following: probability n over d. So again, we have a constant d here. So let's make it d naught. Okay. So n over d. So when we do n over d greater than e power minus n epsilon n square m c over 2 minus d naught, when you take the ratio, right? We take the ratio. So these are two high probability events.
I think you are going to go further, right? Let's say you start with this.
No, so it's already done, right? So we already showed that the denominator is large with high probability and the numerator is large with low probability. So we are going to just take the intersection of these two events, right? Yes. Once we take the intersection, in the intersection we have n over d large with small probability, right? And the probability would be essentially, can anybody tell what the probability will get? Essentially, it would be so all we are doing is probability A intersection B complement is less than probability. What we are doing here?
Complement union B complement.
Just simply A complement plus B complement, right? So this would be just 1 over n epsilon n square plus e power minus c over 2 m n epsilon n square, and both of them goes to 0, so the sum goes to 0. All we have to do is to pick m, the inflation factor, sufficiently large so that this is positive, and that we can do because this d naught here is a global constant. Also c is a global constant as well. Go ahead.
If I take the complement as like the denominator term, so that we get the 1 by n
Yeah. So this is, so B complement is exactly, so A complement is, so let's see. So D is, yes, yeah, so. So again, N over D, we need a lower bound to that, right? So we know that, right, and that probability is less than 1 over n epsilon square. So we just take the sum of that, right?
But that is why you're taking the union.
So union is less than the sum. So yeah.
I think he's asking that what is the complement of the second event where n is smaller or equal to that. He's saying 1 minus. Yeah, 1 minus. But I am, yeah. I have my other question, but I'm okay.
So not okay with the argument, or?
I'm okay the argument because at the end of the day, I want to show that no matter what ratio, probability of ratios bigger than something,
Right.
go to 0.
Right.
That's my purpose, right?
Sure. Yeah.
All of that. I'm
Yeah.
starting my research like that. Okay. And then I have some observation
Mhm.
which I obtained from 1 and 2.
Sure.
How am I gonna combine them in a way that I give this?
Sure. Yeah.
Okay. Okay. I got that part.
Yeah.
That's what
But
we're doing.
but then
Yeah.
can you kind of rephrase your question one more time?
If I define A to be, or maybe A complement to be, the denominator is greater than that term, or say numerator is greater than that term, we need that one.
Yeah.
So
the denominator is less than this guy. The
desired one. So
no, desired one is n over d greater than that one, right?
That's
So this is the desired one. So this is the intersection,
yes.
right?
So one event is numerator greater than that term, like
Right.
one is implied probability.
Right.
That is one event.
Yes.
The other event is denominator is less than e power minus d naught and epsilon.
Right.
That's-
Yes. And both event has small probability.
okay.
Yeah, but
I
if
am
we
I
write
am
that like A and B, if we define A to be numerator greater than this and B to be is denominator is less than this, then that inequality won't be.
not that. B complement is there.
Yeah, just choose B complement to be that. Yeah.
Because you can get ratio greater than that if you don't assume B complement is that.
Okay, if we consider B complement is like B
Okay.
power minus then the intersection, the numerator is
No,
greater than.
no.
Okay, I get it now.
Yes, you are a
I
little,
get it now.
because that ratio must be greater than that only if
Yeah,
you
yeah.
define B complement is that guy.
Just choose A and B accordingly, right? I'm just going to leave at that. All right. So I'll move on. To the next result. So what happens when alpha is exactly equal to 1? So right, so this is our original posterior. And let's try to see whether the same proof technique works. And like we discussed last time, if we look at the numerator for alpha equals 1, so it's going to be simply of course, we cannot use the Renyi divergence trick simply because it's defined for alpha between 0 and 1. So let's just take the expectation of the numerator as it is. We can push the expectation inside. The expectation of the log likelihood ratio. So what's the expectation of log likelihood ratio? It's just 1, right? So end up getting 1. So there is no exponentially small probability that you are getting last time. So what we do here? So you have to take a note here that the numerator is over B complement, and we are not really exploiting the fact that in B complement, theta is far away from theta naught. We are simply taking an expectation which doesn't really matter. It's always 1, no matter how far theta is from theta naught. So this is not really a good strategy in terms of the proof technique. So we need to change the proof technique in a way that we take advantage of how far theta is from theta naught. So Markov's inequality will not really work here. So if you directly take expectation, it won't really work. So this brings us to a very interesting like theoretical development back in the 70s, 80s, and 90s by Burge and Lacam. And the topic is called minimax testing. So the idea is to kind of bring together tools from hypothesis testing in order to show that the numerator is small with high probability, even if we consider alpha to be 1, right? So we simply can't really take the expectation of the numerator, but then what we do is we will take the expectation of the numerator, but subject to theta is far away from theta naught, and we are going to show that that quantity is small. So somehow we need to be able to concentrate in the region that theta is far away from theta naught. Otherwise, we can't really show that the numerator is small with high probability. So let's do that. So again, remind ourselves what we are aiming here. So probability of B complement given xn, we need to show that this goes to 0. And remember, this probability is with respect to now alpha equals 1. So we are not doing fractional posterior at all. We simply focus on the original posterior. And in order to analyze this one, note that the denominator result is always going to be true, no matter whether alpha is 1 or strictly less than 1. So probability that d is larger than e power minus d naught n epsilon n square is always going to be 1 minus 1 over n epsilon square under the prior mass condition. So let's kind of have this result on top of that. So now this d naught depends on alpha somehow, and alpha equals 1 there. So it doesn't really, so d naught stays a positive constant there. Okay. So we need to show this kind of result. So we are going to use a strong hammer, like borrowing ideas from testing. So I'm just going to, so remember, so this result is true under the prior mass condition. So here comes the second condition that you need. So under prior mass condition, this holds. So now second condition, and this is called the testing condition. And this is more existential, as I'll write it, and then maybe time permitting, I'll verify this one for particular examples. Okay? So this is an assumption. So it would be a little bit cryptic, but bear with me. Once we have the statement, then we'll explain what exactly that is. So there exist two sequences. So the first sequence is a sequence of test function, meaning that it's a mapping from the sample space to the unit interval, right? And it's indexed by the sample size. So phi n is a mapping from the sample space, which we denote using omega. And since we have n random variables, we have a product space, right? Omega n to 0, 1. Think of phi n as a function of the data that spits out a number in 0, 1. And I'll kind of give you the intuition what phi n means here. Okay, so this phi n has to satisfy something. So I'm going to write that down. And then we also have another sequence which we denote by script fn. And this script fn is a subset of the parameter space. Okay. Okay. So script fn contains theta, lots of theta, and phi n's are functions. So we need to be careful. Such that, so here comes a little more complicated assumption. So I'll not go down here, but maybe kind of move back and forth here. So again, when we are doing alpha equals 1, let's make our life a little more general. So earlier we have been working with the alpha divergence. This won't really be meaningful here because alpha equals 1. So we can't really define the divergence. Well, there's a way, it gives you the Kehl divergence, but we'll not go there. But instead, we'll work with a general metric D. So this B complement is defined in terms of a general metric, theta, such that D of theta, theta naught greater than M epsilon n. Okay, so the scaling factor is still there. Now we are going to make our, yeah, go ahead. That's a very good point. So typically, D alpha has a square order. Think about Kehl divergence. Kehl divergence between two normals is squared of L2. So that's why we have epsilon n squared there. So the parity of D alpha should, D is essentially square root of D alpha in a sense. Okay. But that's a really important point. Okay, so we are going to make our life even more general. So instead of considering parametric families, we can just look at the densities as a whole and call P naught to be our true density and P to be the model that we are fitting. So we are now in a completely non-parametric world. Yeah.
All parameters become probability densities?
Right. So our script theta is really a collection of probability densities now. It doesn't really matter. You can parameterize it when necessary, but let's make this general. Okay, anywhere we need to make P instead of theta? Okay, we are good. So we are looking at this kind of neighborhood, and D is like up for grabs here. We can choose whatever D based on the condition that we are going to assume now. Okay. So there exists two sequence phi n from omega n to 0, 1 and script fn, which is a collection of densities now. Now the script fn is called, there's a name to it, it's called a sieve. Sieve means an increasing sequence that is essentially going to cover theta as n goes to infinity. Okay. Such that we have a condition which is called exponentially consistent sequence of test. It simply means the following. If you take the expectation of phi n is a function of the data, so it makes sense to take the expectation of phi n. And so this condition is true. Can all of you see beyond this line?
From screen.
Oh, from screen, right? Yeah. And let me just write down what the second condition is, and then we'll discuss. It's just a bit complicated, but just bear with me, I'll explain. we are taking expectation of phi n. Phi n is a function of the data with respect to p naught, and that's exponentially small. In the second line we are taking expectation with respect to p, meaning the data is generated from p, and then we are taking 1 minus phi of n. Now, this p can be arbitrary, so we are taking supremum over b complement. So remember, b complement is this neighborhood, outside the neighborhood, right? Intersected with this phi n. Okay. So this is essentially the stuff that we need to assume in order to show this thing happens. So what exactly is going on? So let's use pictures now. Okay. Now, in non-parametrics, we can't really write it, but it helps to give an analogy. So this is p naught, and this neighborhood is b. Okay. D p naught less than m epsilon n. So this radius is m epsilon n. Okay. So the entire space is your theta, set of all densities on which your prior is, right? And we want to show that the posterior probability of the complement region is small. Okay, so what we are doing is the following. We are assuming that take any point outside this neighborhood, okay, but intersected with fn. So fn's are something like this. So let's use a different color. So this is f1. This is f2, slowly growing to the entire parameter space. Okay, it won't look like this, but maybe at f infinity it will cover theta. It's like filtration in martingales. Yeah, go ahead.
So coverage is like for as the sequence increases, you can define a set of finite balls or like balls around points such that.
That's one way to construct that. Yes, yeah, that's one way to construct, and in many cases that will actually work. In many finite, yeah. Okay, so this fn is clear, right? So then what we are looking at is the following. So let's say we are at particular n, right? So this is the fn at particular n. We pick a point p here. Then we consider a hypothesis testing between p and p naught. So p naught is your null hypothesis, that's the data is coming from p naught. Your alternative hypothesis is your data is coming from p. And this phi n is essentially the indicator of the rejection region that we are considering. So we are not making it precise. We are just letting phi n to be any number between 0 and 1, and that includes randomized test as well, right? Because it can take a number strictly between 0 and 1. So we're not like making it very clear. We are just assuming that there exists a test. Test means a rejection region for which we can consistently distinguish between p naught and p. So now let's look at what is the expectation of p naught of phi n. So this is the type 1 error. If phi n is the indicator of the rejection region, this is the probability of rejecting the null hypothesis if p naught is true. Type 1 error is small. And if you look at this guy, this is type 2 error. But type 2 error is going to depend on what alternative you take, and that's going to be taken over the entire p intersected with p. B complement intersected with fn. And supremum of that. So the supremum of the type 2 errors, small, and type 1 error is small. So this is essentially the, yeah, go ahead.
So I like classical frequentist testing.
Yeah.
We're actually at one error also versus to 0. Whereas typically in frequentist it would just be control maps on 0.
You are right, but again, as we as we increase n to infinity, then type 1 error will go down, right? So I mean, typically when you're doing fixed,
I guess you could have both.
yeah, you can have both of them go to 0 at the same time. Yeah, just because sample size is going to infinity. So so both will not go to 0. Let's say if p naught and p both depends on n somehow, and the discrepancy doesn't. If the discrepancy increases with n, then both will not go to 0. But if this stays the fix, and stays fixed. And if we increase the sample size, then of course we are going to get some separation. All right, so again, the second condition is a little mouthful here, but I'm going to verify it for special cases, time permitting. So, but let's assume this one and try to prove the result first. Sure, yeah.
So here we are going to use the second condition for the one and the left, right?
Yeah.
Since these are the like the existence statements.
Yeah. These are existence statements. Script fn exists, pn exists. So that's what we are going to assume here. But you need to be able to come up with fn and pn for specific examples. Yeah. Yeah. So there are examples where you can't really find pn, right?
Yes, exactly.
There are examples like that. Okay, I'll keep this assumption. Okay. All right, so let's start with the analysis. It's really not too hard once, because this second condition does the hard job. The proof is relatively straightforward. So pi of b complement given xn. So now we are going to look at the expected version of this, right? So remember at the beginning of the definition of posterior contraction rate, we said that we are going to work with the L1 convergence. So here is it L1 means taken expectation with respect to P naught. Okay. All right. So here is the business that we are going to do. So all of you agree with this? So we had the probability here, but we just bounded it by 1. Right? So this is where we kind of like partition out the bad part, right? So we just look at the good parts. So you know that 1 minus phi n essentially controls the type 2 error over the complement region, right? So this is small by a sum. All you have to do is to make this one small. So let's denote this by 2. The 2 will look like pi. So let's do term 2 or T2. Okay. All right. So the way to do this is to kind of expand out the posterior probability. So expectation of P naught 1 minus phi n integral b complement e power ln theta p naught there's no alpha here, it's just 1. Right? Okay, so now we are going to again use some of the things that we have proven before. Can anybody tell what an is? We simply intersected So when we take the expectation with respect to P naught, we are taking expectation on the sample space, right? And this AN has to be a subset of the sample space. And then we kind of sieved it out. So what would be a good choice for N? Where denominator is not too small, right? So there exists a set AN, we already proved that, where the denominator is not too small. So let me kind of like recap that one more time. So what we have proven is the following. Probability that D is larger than e power minus n epsilon n square. There's a constant D naught here. 1 minus 1 over n epsilon n square, right? So we have already proved. So this set, I'm calling it to be n. N complement, so this probability is already less than 1 over n epsilon n square. Okay. All right, so that makes our life really easy. So we know that the denominator is greater than this guy. So this goes up. Need to make room for the denominator. Okay. Okay, so this is we are going to denote by T21, the first part of T2, and we have already proven that T22 is small. So we are not going to worry about that. So T21 is now less than or equal to, so this is a constant comes out. And the indicator has done its job. We're going to throw it out. All right, so let's now look into this quantity a little more closely. We need to make use of second condition, but then it's expectation with respect to P naught. So what can we do here? Okay, so now in order to kind of gear ourselves to use the second condition, we take an intersection with phi n. Then plus we need to kind of have the remaining stuff as well, right? Okay, so when we write down the remaining part, we are going to use a set of inequalities as well, right? So this is unnecessary when we look at Fn complement. So we need to have the Fn complement here now, right? So the little piece in the sample space that parameter space that we kind of left out. And then we push the expectation inside. That gives us 1. And we simply bound it by probability of Fn complement. All of you agree with this? So T21 can be upper bounded by this guy. Right? So I haven't really done too much, right? So in the second part, I have discarded 1 minus phi n, push the expectation inside. We know that this is going to give you 1. Then we are just left with pi of Fn complement. So B complement has its intersection there, but we kind of like make it even larger.
I have a question.
Sure, yeah.
I understand things are here because FN is a sequence of distributions.
Well, Fn's are subsets of the parameter space, subsets of the densities.
I guess even in this,
Mhm.
parameterized setting, FM would just be a sequence of, say, real parameters.
Right. So FN will.
So like the probability attached to any particular sequence like this, unless we're discretizing
No.
the parameter space, like the complement's going to have probability 1, and the
Yeah.
intersection is going to be a countable set. So it's
Right. Sure. Yeah. So FNs are essentially not sequence of the alternative, but it's a class of alternative altogether, right? So typically, let's say you're doing normal mean estimation, your data is so FNs are going to look like this. Theta such that norm of theta greater than some mn, and mn is going to infinity, or actually less than mn because it's going, right? So it's not going to be like a particular sequence of alternative. Yeah. Collection. Yeah. Yeah. All right. So as you can see, then T21 has two parts. We call it T211 and T212. And T212, we need condition in order to kind of make it small. So that's where the third condition appears. Which is essentially e power d naught n epsilon n square pi of Fn complement converges to 0. And d naught comes from the prior mass condition, right? So this is exactly the condition we assume, just to throw it out. The reason we can make it smaller simply because of this, right? So Fn complement would be norm of theta greater than Mn in particular example. And we can kind of choose Mn to be large enough in order to kill d naught in some sense. But then if you choose Mn to be large, you need to pay a price here. Right? So we need to be mindful about that. So okay, so this part is going to, so T22 goes to 0 by assumption by third condition. Now we are left with T211. So this is essentially the type 2 error condition. Can anybody see that? Why it's the type 2 error condition? We push the expectation inside, right? Now it has the log likelihood ratio. So we cannot, we don't throw this term out. If you throw this term out, we'll get 1 because expectation of the likelihood ratio is 1. So we keep this guy, right? And T211 is exactly going to be I'll pause for a moment here just to kind of let this sink in. Yeah. So we have an expectation with respect to P naught. How come we have an expectation with respect to P? It's simply because likelihood ratio, right? So when you take the when you expand everything out, so expectation of P naught means we need to have a product of P naught, right? That gets cancelled with this term. Then we are left with product of P's, which give you this expectation. Right? And then we know that we can make the supremum of this quantity small. So this is less than e power d naught n epsilon n square times e power minus n m square epsilon n square, and choosing m to be large enough, this one goes to 0. So this is essentially the contribution of Ghoshal and van der Waart in the late 90s and the early 2000s. But then, of course, we need to kind of verify all these three assumptions in specific problems. So there are three conditions, as we can see. The first one is the prior mass condition that ensures that the denominator is not too small. Second one is the exponentially consistent sequence of test condition and the existence of phi n and fn. And third condition means that phi n complement is negligible as long as prior is considered. Yeah, go ahead.
So, if we look at the T2
Mhm.
from the above, the forwarding,
Mhm.
to use this, so my question is this.
Yeah, go ahead.
I'm setting different assumptions.
Sure, yeah. I mean,
Yes, and then here I am saying that premium P in B complement
Mhm.
satisfies that without going to FN business.
okay. So you're taking,
Yes, I am doing whatever you did in the last step.
okay,
Exactly. I'm writing that probability in terms of right what you did this step.
so you're intersecting with fn or?
I'm not like the. I don't know whether if you are going to give me like a break, I can ask you to.
I mean, consider this as a break, right? So
okay,
yeah, you
yes.
can ask so that,
So
yeah.
what that like here without T1 2 1.
Mhm.
Okay, not next step. So I am saying simply is that
Maybe you can just,
yes,
yeah.
exactly. So here what I'm assuming, okay, I have this one. So I can write that one like this, right? Without just be
Sure.
be complement.
You still have the denominator to handle, right? But yeah, so then this should be posterior of fn complement intersected with, yeah, this would be posterior of fn complement, yeah.
Fn posterior of Fn complement.
Yes. So now we have the prior.
Okay.
So the main reason we are kind of like having this condition is because we don't want to make any assumption on the posterior. Then we could have assumed that the posterior is consistent, right? So we want to make all the assumptions in terms of the prior itself and the likelihood, not any condition on the posterior.
Okay, we needed that thing to get rid of the denominator, right?
Yeah, we need to
Okay.
be able to, and that's the reason this e power business comes in, and then we are left with a term which is
Yeah, that's the thing. Need to tackle the denominator somehow.
yeah.
Yeah, my question more like there is no way to
Yeah, I mean, I understand. Then it would be pi of fn complement given the data, and then we have to assume that the posterior of that one goes to 0 sufficiently fast, which is, we don't want to assume anything about the posterior. Yeah. Yeah.
This is not just T to this and this one.
Mm-hmm.
So that controls the denominator.
Yes.
So that's coming from the one assumption we did here. So yeah, what I'm trying to say is that I have this still.
Mhm.
Okay, I put this one out as you did here, and I ended up coming here. The only problem is that how am I going to change P0 to P?
Mhm.
That's like essentially what you are doing. The minute I get here, you are using it.
Right.
Okay, I am saying that if I just have the B complement,
Mhm.
I still can put this one here with this.
Yes.
And then if I assume like without the F business, just supreme over that is satisfying that.
I see. Of course. Yeah. Then fn would be fn is the entire theta.
Yes,
Oh.
exactly.
Yeah. So your question is, why don't you choose fn to be theta? Yeah, go ahead. I'm not,
Yeah.
the assumption doesn't say that fn should not be theta.
Yeah, exactly.
Yeah,
That's
so
the
it's
thing.
included. What you're saying, the thing is that you can't verify the second one. The space would be too large. So, okay, so let me give you an example. So typically spaces like this. So normal theta 1, theta is the entire real line, right? The alternative null is theta naught, alternative is the entire real line. So you won't be able to verify the type 2 error condition unless you kind of like make it bounded.
That's so, yeah,
Yeah.
okay. Yes.
Because typically this the type 2 error will increase as fn goes to infinity, and then so and the separation also increases, so it's hard to all right. So let's take out the time. So we'll take 5 minutes break and then we'll continue again. Yeah, go ahead.
Our condition also is that the prior is very behaved, right?
Yeah.
It does affect
For instance, I mean, if you take very heavy tail prior, then this won't really work.
assigning more mass towards the true wall.
So it doesn't say anything about the truth, because we are fn complement is the tail, right? So this is the tail condition more. So this is the prior mass condition. So this says the prior should assign sufficient mass around the truth. This says the prior should not be heavy tailed. And this condition says that the likelihood should be well identified. That means we can, I mean, think about likelihoods which are not very well identified. So we can't really get consistent sequence of tests there. Resume a discussion about like verifying this condition, because this is the condition we typically, so the recording is on, or okay. All right, so so general recipe for verifying second condition. So now we are going to, so right now our treatment is very general. So our distance is d. We haven't really made any assumption, but somehow the role of d is in here because we measure the discrepancy between null and alternative in terms of d here, because b is essentially in terms of d. So how to verify this second condition? Okay, so we'll do a step-by-step approach. So here is your p naught. Okay. Just to fix ideas, we look at total variation distance, okay, between two probability densities. So T V of between P1 and P2 by definition is simply P1 minus P2 Reason square. It's 1/2 absolute value of P1 minus P2, which is the same as P1 greater than P2, P1 minus P2, and which is again the same as P1 less than P2, P2 minus P1, d lambda. Okay. So let's see whether we can kind of work this out or not. All right, so so B complement, so we have the picture here. This not, and this is the ball that we measure in total variation distance, and so let's say this is our P, and of course we have chopped it off, so this is our Fn. Okay. All right. Of course, this distance is larger than the radius by definition, so that's what we are going to utilize. So for the time being, let's just talk about these 2 points in the parameter space, and let's call it P1, just to kind of make our life simple. And P naught has a ball around it, and P1 lies outside the ball. And this distance is dTV P naught P1. So let's just ask the very simple question. So let's say we have data points coming in, right? And we are going to test between the two hypotheses that P is P naught versus P is P1. So how do we come up with the most simple test here? Likelihood ratio test, right? So that's the simplest thing that we can do. So our rejection region is going to be product P1 xi over P naught xi greater than a constant. Okay, and let's just say the constant is 1. Okay. Right, so we are going to find out our test function is indicator Rn. Okay, and we are going to find out what's the type 1 error of this test. Can somebody help me with the type 1 error? Probability under P naught, the product P1 xi over P naught xi greater than 1. Then you apply Markov's inequality, and then you'll get 1 doesn't work. Right? When you apply Markov's inequality, it's the likelihood, so you just get 1. So I'm just going to use a very simple trick. I take square root on both sides. Okay. So then we apply Markov's inequality. So when we apply the Markov's inequality, what's the expectation of this guy? So remember, this is the whole idea of fractional posterior, considering the fractional posterior. But we didn't consider the fractional posterior here, but the introduction of test functions make our lives easy. Right? The test function actually helps us concentrate at the right region of the sample space. So when we apply Markov's inequality, we get affinity of P1, P naught whole to the n. And this is nothing but less than e power n times log of the affinity, which is less than or equal to e power minus n times one minus Hellinger square sorry, there should be a log here. There is no negative sign. Twice n log of 1 minus h square, which is less than using log of 1 plus x less than x. This is less than twice n the Hellinger square. Okay. We have done this sort of calculations before when we looked at the fractional posterior. So we are trying to bring the same ideas here. Right. So then we know that we have this inequality Hellinger square less than total variation less than the Hellinger, right? So that basically means that this is less than e power negative twice n dTV square. So we are done with the type 1 error. Okay. So now let's look at the type 2 error. So expectation of P1 of 1 minus phi n, which is the complement of this guy. You know the drill, right? So you flip things and then use the same thing. You'll also get dTV P naught P1 square. And we know that the distance between P naught and P1 is less than epsilon n. That means this is always going to be less than or equal to e power minus n epsilon n square. Okay. There is an m there if you inflate the neighborhood, but yeah. So we have the type 1 and type 2 error condition satisfied with total variation distance. Okay. Also Hellinger as well, because the Hellinger comes way more naturally. But this is between just 2 points. What will happen when you have to deal with so yeah, let's not erase this one. Yeah, this doesn't depend on Fn because they're just 2 points, right? Okay. So here is the general idea when you have to deal with, so we again, the type 2 error is defined as the supremum of all those pointwise type 2 errors. So here's, since there are 2 points, I don't have to do any work. So all right, so let's kind of make it a little more general. We'll go one step at a time. We also consider a ball around P1, which is disjoint from this ball, of course. And then our alternative is now, yeah. So this is dTV set of all p's such that dTV P P1 is less than, it has to be smaller than this distance, TV P naught P1 over 2, let's say. And let's call it U. How to make sure that the test that we have developed works here, right? So we already developed a test which based on one single alternative, right? So our test is indicated the likelihood ratio greater than 1. So now this becomes a bit complicated because we are not just looking at one alternative point, but we are looking at a multitude of alternative points. So we have to, so the type 1 error is easy, right? But type 2 error becomes hard. But you can do it actually. Again, I'll not go into the details. If you want to read more about it, there is a beautiful literature on, again, chapter 8 of the document I shared. Again, it's based on the idea of minimax testing, and they kind of nicely show that no matter what you take, as long as the alternative region is a convex set containing P1, this sort of tests work. Okay. It has to be disjoint from the ball, of course. Yeah. Go ahead, Alex. Yeah.
No, I haven't.
Oh, okay. Right. So now we are down to testing between P naught and a ball. And then what we claimed is we can make it more general, any convex set works. But now we need to do it for B complement intersected with Fn. So this sort of sets is not convex. It has a hole in here, right? So you cannot really apply the chapter 8 there. So the idea is what you do, again, it's a very standard technique from Budge-Lacan theory. So you simply cover the alternative region. So you simply cover B complement intersected with Fn with balls. Now, this is very important. How can we guarantee finiteness? And that's why Fn cannot be entire theta in most examples, right? But if you have something like in the normal example, if you have norm theta less than Mn, this can be covered by finitely many balls. Yeah. So it's totally bounded. So you don't need to be compact. It just needs to be totally bounded. Yeah. It's called pre-compact, right? Anyway, so so this is the ball around P naught, and you are testing with multiple balls, right? So for P naught and the center of each ball, you have one test. P naught center of another ball, you have another test, right? So let's say you're able to cover the space B complement intersected Fn with capital N Fn many balls. Okay. So you have like N Fn rejection regions now. How to combine it with a single rejection region? So that's because at the end of the day, we can't really work with N Fn many tests. We have to make one test out of it. Any ideas how to combine it with Siddharth? Yeah, it's the maximum or the union of the rejection region. Yeah. Yeah. So so let's do that. No, when we combine all the maximum, the type 1 error is going to change, right? Because union of regions, the type 1 error will inflate, but type 2 error is actually going to go down. So
I guess I meant like the type 1 error is sort of easy to control because
yeah,
you're only ever looking at whether you're scaling a bicycle concurrently.
Exactly.
Closest binary.
Yeah, yeah. It's more easy to control. Yeah. The type 2 error is where we need the chapter 8 of the reference here. Yeah, go ahead.
The assumption is that you can cover the entire distance
Yeah.
With finite number of balls.
Yeah.
So that's where it ensures restrictions on your parameters. Because
Right. I mean, or the restrictions of how you can choose Fn, right? Your parameter space can be infinite dimensional or very like large or whatever. Then your Fn should be chosen in a way that this the covering number of Fn should be finite. It's a pre-compact test. And in many examples, you can do that actually. So yeah.
Yeah, that should not like them supremum of the covering set.
The original area, right? Yeah. Yeah. For each finite n, you can cover, but the limit you can't cover, of course. Yeah. All right. So let's kind of try to make the idea of choosing the maximum a little more concrete. So let's say we have tests P n1, P n2, dot dot dot, phi n Fn. right? For testing between P naught and the center of each of the balls, that's going to cover the space. Then we simply take our global phi n to be just max finitely many sets. We can take the maximum of this one. So once we take the maximum, we need to be able to work it out, work the type 1 error out. So expectation of P0 of phi n. So we are going to be lazy and just apply the union bound. Bound max by the sums, or in terms of sets, bound the union by sums. So it's going to be n fn, cardinality of that, e power minus n m square epsilon n square. Yeah, go ahead. Yeah, same epsilon square. Yeah. And then you look at a point in the alternative. Now this is going to be very easy because union, right? When you look at alternatives, type 2 error is bounded by type 2 error of one of those tests. Just take the first one maybe. So it's a very important concept. Type 1 error is the accumulation of all of them, but type 2 error, you can just bound it by one of them because you're taking 1 minus of that, right? And this is anyway, we have already shown that this is less than e power minus n epsilon n square. So all you have to do, ensure that this first inequality goes through, is to make sure that the covering number doesn't grow up too fast. If it grows too fast, to kill this term off, then it's not good. Yeah, go ahead. Yeah.
Total bound, like I was going to ask, what's the border point if you don't have total bound? But you already said that covering number.
Yeah. Covering number is different for totally bounded sets, right? So you don't need compactness. Yeah. I mean, think about it. In the normal example, we don't put, theta strictly less than m, this is not a compact set. It misses the boundary, but it's totally bounded. So yeah. And it doesn't matter because if you use a Gaussian product, the probability on the boundary is 0 anyway. So okay, so if you're good with this, I'll go on to just do the normal example. Nobody uses this sufficient conditions for normal example because you have the close from posterior anywhere there, but it kind of helps us get the main ideas. Again, I swept a lot of things under the rug by deferring to chapter 8, but if you have time, go over that. Okay, so simple problem. x1, x2, xn follows normal theta 1. Theta follows, let's say, normal sum theta mu theta and sigma theta square. Theta naught is the true parameter. We need to show that the posterior is consistent with theta naught. That means we need to first start with a distance metric. The standard one is the Euclidean. And then we are going to look at again, here you can do explicit calculations. So we don't use all those sufficient conditions. So the sufficient conditions are really helpful if you have complicated likelihood, complicated prior distributions. There you can just verify the survey. Here you can do everything pretty explicitly. So, all right. So what do we have to verify here? So whenever you start with an exercise to do posterior consistency, first look at how difficult is to compute the KL and V neighborhood, because that's where I think the major challenge will lie. And the test function business for parametric problems really straightforward. As you can see, Hellinger will give you the test pretty easily. All you have to verify that the sieves covering number don't grow too rapidly, right? So KL and V neighborhood. Can anybody tell how will the KL between two normal densities will look like? I've made your life simple, one variance, right? So I think a lot of the terms are going to vanish. And if I'm not wrong, it's going to be just norm of theta minus theta naught square over 2. But I'm, yeah, probably. So this is the easy part. The harder part is to verify this one, actually. So if you do the math, it would be, it's not too hard again. You have just log of the ratio and things are easy for normal. So again, don't take my word for it. I'm pretty much sure about this one, but again, I may be like not correct with the constants. So all you have to verify is the prior, which is the Gaussian here, prior probability of theta minus theta naught. Keep in mind that both of them can be made small if we assume theta minus theta naught to be small, right? Right. So because epsilon is a very small enough quantity, right? So this won't really matter. So if you make theta minus theta naught, norm of that to be small, we can make it smaller than epsilon square, and we can also make it smaller than epsilon square, right? Because this is like bounded by 1 anyway. And the way, so as you can see, this is relatively easy for normal problems. Again, you can, so it becomes harder when you have a covariance matrix in multiple dimensions. One uses the Anderson's inequality. But if I have to do a very bonehead calculation, then it should be lower bounded by the volume. If D is 1 here, the volume of this neighborhood is of the order epsilon n times the infimum of the normal density in this neighborhood. Think about it, it's the integral of this neighborhood, right? So I just lower bound by the volume times the infimum of the density. And the infimum of density around a small neighborhood of theta naught is a constant typically. So it's greater than e power, greater than just epsilon n, which is I just write it in a more fancy way. Okay. It's the T.W. Anderson multivariate analysis book. So that Anderson, yeah. Okay, so then we need to show that this is greater than e power negative n epsilon n square. So it's kind of cyclic, right? So we have epsilon here, need to show that this is less than epsilon n square. So we keep the condition here. We'll come back to it once we have dealt with the other ones. And as you can see, you cannot have this for all epsilon n's. For this to hold, you need log of epsilon n has to be larger than or equal to epsilon n square, which means that log of 1 over epsilon n has to be less than n epsilon n square. This is a pretty loose restriction anyway, right? So this is of the logarithmic order, and this is at least some amount of polynomial is there. It's easy to verify. So now let's look at the main the other one, the test function condition. Go ahead. Yeah. This one? Yeah.
First, we call the lower bound.
Oh, okay. So I hand waved a little bit actually.
They are constant.
Yeah. So there are constants floating around. So this is an integral over this region of the normal density, right? So that is lower bounded by the volume of the neighborhood, or just the size of the neighborhood, which is of the order epsilon n. So there is probably 2 epsilon. I don't care about the constant. And then you have the infimum of the density within this neighborhood, and that's typically a constant. So there is a constant here. Yeah. Okay. Right. So phi n, we are going to use the same phi n that we talked about, the total variation distance, and total variation distance between the Gaussian density, it's also like equivalent to the L2 metric. So all you have to do is to come up with a script fn, and then kind of have a way to control the covering number, right? So let's do that. We take our fn to be set of all thetas for which the, so here since we are in one dimension, norm is just the absolute value. So some an, okay, we are going to choose an later on. So what's the prior probability of fn complement? What's the probability that the absolute value of a Gaussian is larger than n, for large n? Tail bounds for Gaussians, right? Typically of the order e power n square, Gaussian tails. And let's try to cover this space with balls of radius epsilon n and look at the covering number. So what was our notation for the covering number? NFN, right? Yeah. So can anybody tell what would be an upper bound for the covering number? So you have an interval, right? Of size twice n. Yeah, you need to cover it with epsilon balls. So then just maybe have some overlap. Because balls are open, right? So you don't have overlap, you miss out 1 point. Doesn't matter though. But so roughly of the order, how many balls you need of size epsilon n? That's it. So here balls are essentially intervals. It doesn't look like this. So these are just intervals. Say that again.
It's kind of, since you said it's overlapping, it means we need more, but order.
By 2, yeah. Do it by 2, yes. Yeah. So of the order n by epsilon, you're right. Okay, so we are essentially done. Patch up things. So let's so expectation of P naught 1 minus phi n is going to be upper bounded by an epsilon n over epsilon n e power minus n m square epsilon n square. Sorry, it should be just phi. Right, so I already have the tests ready. We can just use that and have assumptions on the covering number. Right? Okay. So these are already true. All you need to make sure that this is not growing to kill this term. So this is one condition on an that you need. There has to be a counteracting condition, which is pi of fn complement should be less than or equal to e power minus d naught, maybe a little faster, to kill the d naught quantity. How about this? We need. Right? So if you have this one, of course you have this condition. Right? And that helps us to choose a. Right? We need e power minus an square less than or equal to e power minus d naught plus 1 n epsilon square. So n has to be larger than or equal to square root of d naught plus 1 n epsilon n square. And as you can see, this is not too bad. It won't really kill this term. This is exponent, right? Yeah. I mean, this is just a polynomial, and this is exponential of, so it won't really hurt. By a constant, yeah. You're right. Everything is in the constants here. Yeah. Right. So we are able to choose n. We are able to verify the third condition by that way. Second condition is also verified. Now going back to the first condition, we just need epsilon n to be log of 1 over epsilon n to be smaller or equal to n epsilon n square. So let's write it here. So let's circle the important quantities. So this is one important quantity that we would need. And of course, we cannot take n to be arbitrarily large. So just make it equal to, because if we take arbitrarily large, then this won't really go through. So fix n to be that, and log 1 over epsilon should be smaller than n epsilon n square. So we are doing this because we want to arrive at a contraction rate here, right? what choice of epsilon n would verify this one? So if you just substitute, typically it's a parametric problem, right? So 1 over root n would be good. Typically for parametric problems, 1 over root n is your choice, is the minimax, right? So you substitute 1 over root n here and you're screwed, kind of. Can you see why? This condition won't be satisfied. This is log n and this is just 1. So you don't get 1 over root n, but you have to inflate it a little bit. So typically you get log n over root n. So if you I think you can do square root of log n over root n. If you choose epsilon n to be square root of log n over root n, this condition is going to be met. So there is a log n term in here, but it's a matter of constants. You can play around it. So you're able to prove the convergence rate with this one. So you're sacrificing a little bit. Typically 1 over root n is the one that you should hope for, but it's not too bad. And the log n appears because of the proof technique here. So there are refined versions of the theorems that would essentially give you 1 over root n.
Yeah.
And this is just a baby problem. Normal theta 1 who would verify the 3 sufficient condition. If you directly write everything out, you can just do it. But of course, as you can see, one of the critical requirement, I think this becomes more complex. Let's see, if you're in a mixture model setting, how to bound the KL and V divergence is not really easy. For multivariate normals, things are a little complicated here, but you can use, as I said, Anderson's inequality, which gives you much more kind of stricter or like tighter inequality. Test function is already given, but you need to be able to choose the sieves Fn and make sure that your covering number doesn't grow rapidly. Once you have everything, patch together all the conditions and try to kind of guess what epsilon n would be. You already have a guess from the minimax rate, put it there and try to kind of tweak the guess a little bit, just like I did with this. I multiplied with log n to make it happen. So I guess that's about it. I know this is like maybe 0.001% of what's there in the literature. Particularly the testing business becomes very, very complicated if you are working with a neighborhood which is not compatible with total variation of the Hellinger distance. Verification of these two conditions become complicated for complex problems. But I mean, at least you have conditions in terms of the prior that you can verify. Yeah, this is the only way. There are like 20-30 variations of this result, and this is actually a variation. You won't be able to find this in textbook. This is actually a minor variation that I did because it's easy to teach, right? I mean, so yeah, there are many variations. One is still, I mean, depending on the type of application you're doing. For instance, if you're in a parametric world, you have to apply one particular variation. If you're working in function spaces, you have to apply in one variation. If you're working in density spaces, you have to work. Yeah. So, and those are like papers that kind of formulated the variations. So if you do one variation and successfully apply it to class of problems, that gives you a good contribution. Yeah. So, but the main idea is you have to control the complexity of your space using the covering number. You need to make sure that the prior has sufficient mass around the truth, and the prior tails are not too thick. So those are the three main kind of takeovers. Questions? Yeah. All right.
So all of this was to show that the Gaussian prior for
Yeah.
the Gaussian mean parameter is consistent.
Right. I mean, yeah, this is just a toy illustration, but yeah, you can go much more beyond this. For instance, people have written papers with Dirichlet process mixture of normals in non-parametric problems. People have worked with covariance matrix estimation. All the modern problems you can think about, tensor models. Yeah. Anything else? Wait. Oh, okay. Yeah.
Cash. The thing is, the main idea, big idea is to convince the frequentists that we are not doing something maybe wrong.
It's partly true, but more importantly, what I would think is particularly in non-parametric problems, you have prior attenuation, right? You can't just choose any prior and get by. You have to choose prior in a way that somehow is uniform in the non-parametric class that you are looking at. And defining uniformity in a non-parametric problem is not hard, not easy. So, and typically in parametric problems, whatever prior you choose, it's going to be washed away. For instance, in this Gaussian problem, it doesn't really make sense to prove consistency. It's already, you have BVM, which is stronger than consistency, right? But for non-parametric problems, it gets tricky. Let me give you an example. So let's say you're doing Gaussian process regression, right? So you have the bandwidth parameter. If you choose gamma prior on the bandwidth, you will get consistency. But if you choose inverse gamma prior on the bandwidth, you can show that it's inconsistent. So things are that delicate in that level. But if you're working in like parametric problem, it doesn't really matter. Take anything, Gaussian or heavy tails even, you can show that it's consistent. But non-parametric problems is very delicate. So the reason is the hyperparameters actually control the smoothness behavior of the priors, and smoothness is everything in non-parametrics.
You always, in the background, you always think of this consistency before choosing some prior non-parametric.
First, you see whether your method is working well. You don't have to choose prior based on these three conditions. If your method is working well, things are, then you just verify. And in, I think 90 to 95% cases, you'll be able to map it to a problem people have already worked out. So you don't have to do anything, right? But for this, like 5 to 10% problems, you really have to show things work. If you believe that there is a problem, there could be a problem. So yeah. So there are many like standard problems where, you know, okay, this problem can be mapped to this class of problems. Roughly, consistency should go through. I don't have to worry about it. But there are problems where you should have the hunch. Okay, I mean, that here things can go wrong. So there, it's a good idea to prove. Yeah. Anything else? Yeah. Oh, right. Yeah.
So for the ones who want to continue reading about this, what will be the
Right.
next?
So Niladi already uploaded the PDF for the, read that one. Particularly chapter 8, it has all the testing argument, and it has got lots of references. So there are two references that, it depends on the type of application you're doing. So the book pretty much has everything, but the problem with the book is it's essentially a like papers collected together. It doesn't give you too much intuition. So in terms of reading materials, of course, the lecture note, and then for people working in non-parametrics, like more with digital processes and things like that, I would, if you're interested in density estimation, I would recommend I forgot the year. So 2010, it's called adaptive Bayesian density estimation with location scale mixtures by, yeah, you are right, Cruiser, Russo, and van der Waart. If you are working in function estimation, you have to read 2008 van der Waart and van Zanden. This is a beautiful paper. Again, all the sufficient conditions that I just told remains the same, but it has to be developed in function spaces. So there is RKHS and small ball probabilities in RKHS, all sorts of things going on. And if you're interested in parametric problems, but high dimensional, that's, I think, the more common theme people are working on. Again, it's very problem specific, right? So the high dimension can come in various ways, but the building block is proven in Castillo and van der Waart. They worked with the Gaussian sequence model in 2012 paper, and then they kind of extended it to the regression paper in 2015. And this is kind of a like state of the art 2015 paper. Excellent exposition and very detailed analysis about like high dimensional sparse regression problems. So we did work on covariance matrix estimation 2015. Also, we did like networks, maybe a little later, 2016 or something. Yeah, I mean, parametric problems can be all sorts of things. So it's hard to kind of pin down one literature that would kind of serve you all. But, yeah. So yeah, I mean, these are pretty much kind of the main papers. As you can see, the density estimation 2010 paper is actually the culmination of 10 years of work, which started in 1999 by van der Waart. And these guys kind of really took it forward and sealed the deal essentially. I mean, very general results, lots of like citations and all of that. Okay, so anything else? So I'll stop here, and then if any of you have any questions, just feel free to email me, and I'll be happy to answer.